Hello, welcome to Econometrics Melody. In this video, we will discuss about the mean and variance of OLS beta estimate for any variable y. It is the mean that produces the minimum sum of the square of the error. Similarly, if we want to linearly predict the value of y making use of other independent variables x, then the slope of that linear predictor must be the OLS beta estimate. So that produces or that yields the minimum mean square error. The linear relationship between the dependent variable and independent variable, we use this expression, while for the population counterpart we use this relationship where the beta parameter it is given by capital beta and the residual term is represented by epsilon. So this is a theoretical concept. There exists a linear relationship for the population variables, and we take a sample of it and we try to estimate the beta parameters making use of sample calculations. And for population we call these attributes as the parameters, while for the sample we call it as a statistic. And if the expected value of the sample is statistic, if this is equal to the population parameter, then we term that sample is statistic is the unbiased estimator of the population parameter. Now let us move into today's topic. So we have a population model represented by y is equal to xb plus e. So this linear relationship, and we have the sample model y is equal to xb plus e. And we have already seen that the OLS beta estimate that minimizes the sum of the square of the residual. This is given by x transpose x inverse x transpose y. So this is equal to, and let me, in place of y, let me substitute it from the population model. The estimated value of beta, and we know that the independent variable and the residual term, they are orthogonal, and x transpose x inverse and x transpose x, they cancel out, they are inverse to each other. So simply we are left with beta plus x transpose x inverse x transpose a. The estimated beta is equal to the population beta plus this term, and this term is also a beta when we regress e on x, and theoretically this should be equal to 0. And the beta term for this regression, this should be equal to 0 because they are orthogonal to each other. Now if we take the conditional expectation of beta cap conditioned on x, and is this beta is constant, the average of the constant is the constant itself plus, and here condition on x means we know it, otherwise we are treating as if x were constant. So they come out of the expectation like the constant term does. So expectation of e condition on x, this is equal to beta plus, and expectation of e condition on x, this is equal to 0. The conditional expectation of beta is equal to the population beta. So our OLS beta is unbiased because the sample is statistic. The expectation of the sample is statistic is equal to the population parameter, and this is our conditional expectation. Now to calculate the unconditional expectation of a beta, we calculate the expectation of the conditional expectation of beta across all x. So expectation of x, conditional expectation of beta is simply beta, and again it is constant, therefore this is equal to beta itself. Therefore both the conditional expectation and the unconditional expectation of the estimated beta is equal to the population parameter, that is population beta. So our OLS beta is unbiased. It is an unbiased estimator. So we have already seen that beta cap, this was equal to the population beta plus x transpose x inverse x transpose e. So this much term, this should also give beta. So when we regress the residual term with the independent variable x, but theoretically this is equal to 0. X transpose e expression is equal to 0, and we know that. So let us arrange it according to our requirement, and we know that. And let me calculate beta cap minus beta and its transpose. So this should be equal to x transpose x inverse x transpose e and its transpose. So this should be equal to a b c transpose. So this is equal to c transpose b transpose and then a transpose. Therefore Therefore, beta cap minus beta, it is like the deviation from the population mean. This into beta cap minus beta and its transpose. If we take the expectation of it, condition on x, so this should be equal to expectation of, and let us write it is x transpose x inverse x transpose e. So we have substituted the value of this term. Now let us substitute the value of this term from here. If beta, this is equal to beta 0 and beta 1, and if we take beta transpose, this ensures the interactions of all the beta. So this is something like variance covariance. That is why we are taking this into this transpose, vector into vector transpose. So we are ensuring the variance covariance of all the beta estimates. Now this should be equal to, and here we have the condition on x. This is equivalent to treating x is the constant, so they come out of the expectation x transpose expectation of e transpose condition on x, and again remaining x, they come out of the expectation. Now here lies a very interesting theoretical concept that gives rise to homoscedasticity, heteroscedasticity, and the autocorrelation. First of all, let us begin with the homoscedasticity assumption, and then I will explain it later. So x transpose x inverse x transpose, so expectation, this value, let me call it is sigma square I, the identity matrix, and x transpose x inverse. So sigma square is the variance of the population residual term. I'll explain it in a while. And we have assumed the homoscedasticity. So is sigma square is constant. We are left with x transpose x inverse x transpose x, and then again x transpose x inverse. So they are inverse to each other. This is equal to the identity matrix. So the conditional variance of beta is equal to, so when we make an assumption of homoscedasticity, we get this result. So let me take E is equal to E1, E2, E3. We are assuming that we have only 3 observations. So for homoscedasticity, so this is equal to sigma square and I. I is our identity matrix, sigma square I, and let me show it by the help of example. This should be equal to the 3 matrix where the main diagonal elements, they are sigma square, and the off diagonal elements, they are 0. And when we take sigma square common, we are left with 3 into 3 identity matrix. So this is the case of homoscedasticity. And in case of heteroscedasticity, so let me directly draw 3 into 3 matrix. So what does it look like? This is equal to sigma 1 square, sigma 2 square, sigma 3 square, and then the off-diagonal elements, they are 0. There is no autocorrelation. And sigma square, sigma 1 square, sigma 2 square, and sigma 3 square can be expressed as sigma square and some function of x. We'll explore this sometime in the future. And for autocorrelation, the off-diagonal elements, they do have some value. They are not 0. So this matrix, this is equal to, so this is the case of both heteroscedasticity as well as the autocorrelation. Now let us calculate the unconditional variance of beta. So this is our ANOVA. So this is given by variance across x for the expectation of conditional beta plus expectation across x on the conditional variance of beta. So variance across x, conditional expectation of beta, this is equal to beta, population beta plus, so is the value of population beta, so this is some constant, so the variance of the constant is equal to 0. If we calculate the variance of this constant, then this would be equal to 0. There is no variation. Therefore, unconditional variance of beta is simply equal to the expectation of conditional variance of beta. And now let us substitute the value. So when we assume the case of homoscedasticity, then conditional variance of beta is given by sigma square x transpose x inverse. So h sigma square, this is constant. We are simply left with the expectation of x transpose x inverse across x. So this is our unconditional variance of beta. So if x is stochastic, that is, it has some random probability distribution, then this formula holds true. So in this video, we have calculated both the conditional and unconditional exploitation of beta, as well as the conditional and unconditional variance of the beta estimate. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.